So I will start with well, I hope a short presentation. So we did a telecon with Frédéric and Pierre, and after the discussion, we decided of this title. And a few weeks later, when I started to work on the presentation, I found that it was a very ambitious and challenging title. So I decided to show you two examples of challenges that we face for a certain type of experiment. So mainly based on what I'm doing, so spectroscopic measurement. So first, how should we do and how do we do when we deal with experimental, when we deal with experimental uncertainties? Well, first, of course, we should list all the sources of uncertainties and error we have in our experiment. We should try to calibrate at best our experiments, estimate well the uncertainties that comes from the measurement in itself, the data reduction we have to do on our measurement, and then the data modeling or fitting that is needed to extract the quantity we want to derive. In those different steps, you have some choice to make in general and decide what is your continuum, you have to fix some data, some values. And so I think it's important that we explain all the choices that are made during this process, and to keep track of all steps. And I'm not completely sure that we do it as carefully as we should always. And okay, it's not always easy to quantify the different sources of uncertainty that we have, and it's highly dependent on the kind of experiment you're doing. So it's difficult, I think, to find a common way to do that, but maybe we should really think of it. So first example, measurement of dust opacities. So that's a quite simple experiment. You measure your mass absorption coefficient here that you have in the infrared. And it's very simple. It's the logarithm of the transmittance that you measure from your spectrometer. And you have the surface of your sample and the mass of your sample. So deriving uncertainties on this value is quite straightforward. You consider your spectrometer stability, which is not completely well constrained, but you decide for a value, and then the uncertainty on the sample mass, which is related to the precision, the accuracy of the scale that you use to measure your mass, which are small masses in general, so you have to have a good scale. And so you can draw your uncertainties around your curve. Then from this mass absorption coefficient, we want to derive optical constant. And so for that, we have to make assumptions on what are our samples. So we have to make some choices on the grain shape, for example, or on the grain size, and also on the value of the refractive index and the visible range, and on possible agglomeration effect that we can have in our pellet. So this is very practical. So we can try to measure the size distribution of our sample here, but we have uncertainty on this size distribution. We can make electron microscope pictures of our grains to try to estimate what is the shape or the most probable shape. And so once we have chosen all these different parameters, we can estimate how our resulted optical constant would have varied if we let these different parameters that we fixed varied on a certain range. So for example, here you have the error if the value of the refractive index varies from more or less 5%. This 5% coming from a look at databases and at the literature that make me think that it shouldn't vary by more than this value. And then you calculate spectral index with these two values and the relative uncertainty compared to the refractive index that you derive with fixed parameter, with the value that you think are reference value. And you can do that also for grain shapes. You can decide where, if I have spherical grain or prolet grain or oblate grain, and you can vary the axis ratio. And you can see that you have uncertainty on the refractive index and absorption coefficient, which can be complex and which are different for each sample. And then you have, lastly, the error on the grain size, which is a bit more complicated, which was a bit more complicated to estimate. And we had to do a discrete dipole calculation because we consider that we have large grains, so we cannot make some approximation of the theory that was used. And then you sum up everything, and you end up with these uncertainties that varies with they're different from the refractive index, the absorption coefficient, and they varies with the wavelength. So that was the first example. If I have time, yeah, I can. So the next example was the determination of the anharmonicity factor of pH bands with the temperature. So you have spectroscopic measurement on a population of grain, which is embedded in a matrix transparent to the infrared. So you're not in the gas phase and you're in the solid phase. And you measure spectra at varying temperature. And what you want to do is follow the band position with the temperature to be able to derive the anharmonicity factor defined as the slope of of the relation between the band position and the temperature. For that, you have to subtract a baseline to your experimental spectra, find a way to derive a good peak position of your data, and find the relation between the position and the temperature. But it's not always simple. Here you have, for example, one spectrum taken at low temperature over the whole spectral range. So you have 2 micron here and 20 micron here. So first you make a global continuum subtraction, which can be very different depending on people, on who does it, basically. And then when you zoom in, you see that if you want to analyze, for example, this band or this one, well, you may have to do an additional local continuum. So that's a very common problem that you have also in observational data. And so once you have done your 1 or 2 continuums, you end up with this, for example. So this is one band at various temperature. So cold temperature in blue and high temperature in red. And then you wonder yourself, how do I define my peak position? Do I take the peak maximum? Do I take the area weighted peak maximum? Or do I do multiple component decomposition of my band? And depending on the method you choose and on the baseline you have chosen, you will end up with different anharmonicity coefficients. And they do not always overlap. So you have to really, at some point, decide a way to do it, really document it. And in fact, to use this harmonicity coefficient, you will have to do exactly the same decomposition on the other side, or on the you have to use it in the same condition as it was derived, in fact. So you will have to be careful about how you derive the continuum underneath your observation, etc., etc. So okay, all this is not simple, and I think we will have to discuss that after the next presentation.